Wadah putih ya, putih ya.
Good afternoon, everyone. Welcome to our international webinar in coordination with the International Teen Association. My name is Ayuya, and I'm honored to be your Master of Ceremony for today's session. Thank you to all participants joining us. We are thrilled to have you here as we explore innovation, challenges, and the future of the teen industry and its diverse application. Before we begin, here are a few housekeeping reminders. First, please ensure your microphone remains muted during the session. Avoid background noise. Second, if you have any questions, feel free to drop them in the chat room and we will address them during the Q&A segment. Lastly, today's session will be recorded for documentation purposes. Today's webinar will provide valuable insights into the development of teen-based industry and products. We are honored to have experts from the International Teen Association who will share their experience and expertise on how the teen industry continue to evolve and adapt in the modern era. And now, to guide us through the main session and facilitate our discussion, I'm pleased to introduce today's moderator, Pabalga. He will be leading the conversation with our distinguished speaker. Without further ado, please welcome our moderator, Pabalga. The screen is yours.
Okay, thank you, Aziza, and good afternoon, everyone. And please welcome to our webinar on teen industry and its product development. My name is Fabagadin Ian Pardide, and today I will be your moderator for today's session. Before we begin, I would like to express our sincere gratitude to Society of Manufacturing Engineers Student Chapter, Society of Mining Metallurgy and Exploration Student Chapter, Prometindo International Teen Association, and finally, TIMA Industry. This organization made this event possible, and we thank them for their invaluable support and collaboration. As previously mentioned, we are honored to have distinguished speakers joining us today from Great Britain. Considering the time difference, we deeply appreciate their commitment and participation. Our first speaker is Dr. Jeremy Pearce, who serves as the Market Intelligence and Communication Manager at the International Teen Association. Dr. Pearce has over 20 years of experience in the teen industry, focusing on market analysis and strategic communications. He has contributed to numerous publications and has been instrumental in providing valuable market insights to stakeholders worldwide. Today, he will present an introduction to International Teen Association, Teen Valley, and the current trends in teen markets. Please join me in welcoming Dr. Jeremy Pearce. Dr. Pearce, the floor is yours.
Well, good morning, everyone, and thank you so much for joining. It's the evening, I think, you're in. Hopefully you can see my screen.
Yes, we can see your screen, Doctor.
Great. So I'm very happy to be here, and thank you for the opportunity to speak to you about ITA, the International Tin Association, and about tin, this fascinating metal that's actually very important to Indonesia. So yes, I've been in this industry for many years, probably more like 35 or more, I can't remember. And we used to be the International Tin Research Institute, actually. And we were founded in 1935. So we've been more than 80 years in tin technologies of various kinds. We have an archive of more than 30,000 scientific papers on tin that have been published since then. So the ITA is now the International Tin Association, as we've said, and we represent the world's tin producers, including PT TIMA. I'm glad to see one or two here from PT TIMA today. Hello, welcome. Good to see you. Good to see you. Yeah, and yeah. So I personally have visited Indonesia several times and been to PT Timor myself a few times now, and so I'm familiar with the Indonesian world of tin. And let me just start with telling you something about our members here. These are members of the International Tin Association, and you can see PT Timor there on the right-hand side. Also Malaysia Smelting Corporation and Thailand, Taisaco. China obviously is a very large user and producer of tin, so we have Yunnan Tin Corporation there. And in South America, Minso in Peru. So most of the major tin producers are members of our trade association, and our remit is to support the tin industry as it goes forward. So the tin resources are concentrated here in three main belts. You can see here in this diagram. The black one in the middle is the European belt with Africa, the Asian belt, which is over your side of the world there, and the South American belt. So this explains why these tin producers are in these places, because that's where the tin is. So these are some statistics about how much tin is made where, and as you can see here, according to this graph from the data in 2023, the largest tin producer is China, the largest tin producer and user actually. The total amount is about 374,000 tons. It's not a large amount, so compared to other metals. So tin is a relatively small metal, but very, very important. Indonesia, as you can see there, is the second largest tin producer in the world, and in fact is the largest exporter of refined tin in the world. In fact, it can only export refined tin. It can't export the citrate that is mined there, only the refined tin. An important notice here is that, for example, in Europe and the US, it's entirely recycled production. The US itself, and this is a very important point, has no primary concentrate smelting. So you can see here, it's not only important how much tin is made, but as you can see, especially in the world we live in, where tin is made is becoming more important. So here's a bit about tin, and if you don't know very much about it, then welcome to the world of tin. It's an absolutely fascinating metal, and it's used absolutely everywhere, and nobody really knows how important it is. So as you can see on this graph, for example, 51% or half of all tin is used in solder. Well, solder joins together everything, all electronics, all the electrical systems, plumbing in your house, everything is joined together. It's the glue basically that joins everything together. That's how important tin is. What you can see there as well, equally important, and is tin chemicals in the red there, about 16% used a lot in PVC stabilizers, and that's one product that PT Timor makes a lot of, for example, there in PVC pipes, but also many other uses of tin chemicals, perhaps 100 uses in fact. Still tin cans or tin plate packaging, you can see there on the left, 11% in the grey. Very important use of tin to corrode protect the steel and preserve the food so that we can eat it. 8% is lead acid batteries, so that's in your car and elsewhere. And tin copper products are also very important. Those are bronzes and other things. It's a long time since the Bronze Age, but still bronze is still widely used. And lots of alloys as well. Molten tin is used to make glass windows flat. You may not realize that. So you can see here how important tin is to our world. Tin is already vital to the energy and digital transition. So we can see here in the picture straight away how important tin is already. If you look at the solar panel, for example, the silver strip across the front is actually tin. It's a copper wire coated with copper ribbon coated with tin, and it's a vital part. It's a massive new use of tin. As I mentioned, there's about 400,000 tons altogether, now 40 or 50,000 tons of tin used in that application alone. If you think about electric vehicles, the glue that holds that all electronics together there, if you think about power electronics, think about everything actually that's needed for renewable energy, tin has to be very, very important. Not just that, but also digitalization. So we have the 5G and Internet of Things and all the communication networks, everything to do with AI, to do with data centers. Every single data byte has to go through millions of solder joints. So you can see already, it's very easy to understand why tin is already vitally important. But I guess this is mainly the reason why we wanted to talk to you today, is because we are now seeing a lot of new opportunities for tin in R&D. So tin is such an amazing metal. It has so many different properties that it can do lots of different things. And that means that when you're looking at the opportunities and the technologies we need for energy transition, lots of different opportunities are coming along. And we're starting to look at some of those, and that's why we wanted to talk to you today. So George is going to talk a little bit in a moment about sodium-ion batteries, which is one of the latest new energy technologies. That's very, very interesting for tin. But there are lots of others. So, for example, I mentioned already the solar materials, but there's a new material called perovskites, which you may have heard of, which is a very invisible thin coat of tin of material that we put on windows, for example, rather than on panels as they are today. And those are made with tin. Liquid tin also, as you can see there in the picture, is very, very interesting for all sorts of ways to make hydrogen, for example. If you bubble methane through hydrogen, it breaks the bonds and you get hydrogen and pure carbon without producing carbon dioxide, which is very, very interesting and important. Thermal transfer, there's a big new investment in the US in batteries, which use tin metal for thermal transfer. Carbon capture catalyst, carbon capture very important. So tin is very catalytic, so we're seeing that there too. Fuel cell catalyst, many, many other different ones. And we're tracking lots of other new applications in water treatment, electronic materials, even quantum computing, would you believe? Tin is vital to quantum computing. So this gives you an example of the kind of things. We're tracking hundreds of new scientific papers on tin at the moment, and it's very, very interesting. So what we want to do as the Tin Association, we want to create some spaces, and that's why we're so keen to be with you today. We want to open up some spaces where people can come together, tin researchers from all over the world. We can showcase tin technologies and see some of the examples that I've highlighted, show how important tin is going to be for the future. And what we really want to do is encourage those conversations and accelerate the innovation. We're going to focus on two strategic topics: tin and sodium-ion batteries and tin recovery from e-waste. Both of those we think are going to be the two most important topics for tin in the near future. Tin and sodium-ion batteries because it's a huge potential use of tin, and tin recovery from e-waste because we really do need a lot more tin very fast, and we think that's the best way that we can have that new stream of tin from e-waste. We also want to introduce the tin industry, and so in there are all of our tin producer members have exhibit booths inside this innovation hub I'm talking about with lots of presentations. So it's called Tin Valley. It's called Tin Valley, which is like the Silicon Valley for tin. And I think some of you may be already signed up to it, and if you haven't signed up already, then you're welcome to contact Georgia and sign up here. Inside Tin Valley, you'll see these exhibit halls here with the booths like this one, with the universities and companies and startups already showing us some of these new developments. You can have a look through those and together with the information that they have. It's in the auditorium there. We have some live events. We have a live event on tin and sodium-ion batteries coming up shortly in June, another one on e-waste in September. There's lots of on-demand content too. Once you sign up, you can see all of those things. And there's a lot of functionality to network with other stakeholders and other people who are inside this space. So please do come into this space, find out more about tin, and get involved in what we're trying to do. But we also want to do what we're doing today. We want to build tin researcher communities out in regions as well, real-life tin communities. Already we're starting to work in China and start building communities there. But in other places too, in Europe, we have good contacts with Fraunhofer and some of the other universities there, in the US too, and in Malaysia. But here in Indonesia, we're very happy to be in touch with you and to start building these communities there, to start talking and working together about how we can collaborate, how we can get some funding and start to do some exciting and new interesting projects together. So that's our objective and something we can help to do. And we can work with Peter Tima in helping you to do that too. So with these ideas in mind, we think that these are the kind of projects that we might want to think about, apart from what we've already mentioned. These are low carbon projects, for example. So reducing carbon footprint is extremely important for the tin industry as it is for everybody else. and technology is the key to all of those things. So we already tried a lot of different things in the past, and we want to explore those again. So how can we make the process of tin extraction more efficient? How can we use low energy crushing, for example? There are many different ways to crush things that are much lower energy. How can we deal with the fines, which is a particular problem in Indonesia? I have to highlight that one. How can we deal with the fines content? That's causes a lot of losses, and there are ways to do that. Plus, how can we re-engineer the whole process of tin? How can we look at that in a radical new way? And for example, chlorination, instead of taking the tin ore and smelting it to tin and then adding chlorine to make a tin chloride, why can't we just go straight from the ore to a tin chloride? Well, you can, and we've done that already, and we can show you how to do that. Why can't we, instead of using carbon, why can't we use hydrogen to reduce tin and make metal? Well, you can, and a paper has just been published on that from Freiburg last week in Germany. So we want to look at hydrogen to make tin from ore, for example. These are very exciting, new, interesting areas, and we'd really like to talk to you about how we can do those things. We do have the experience. We've already had past research collaborations, including Indonesia with TechMyra and several others there in the past. We can guide the technical direction, we can guide the progress, and we can support the funding opportunities. So that's what I would like to do if we can. Thank you for that.
Thank you very much, Dr. Pearce, for your informative presentation on the International Tin Association, Tin Valley, and the current tin markets. Now it is my pleasure to introduce our next speakers, Ms. Georgia Laurie, a technologist at the International Tin Association. Ms. Laurie hold a degree in chemistry from Loughborough University and has been instrumental in advancing the Tin Valley's initiative and a pioneering innovation hub dedicated to the sustainable development of tin application. Her work focuses on exploring tin's expanding role in emerging technologies, including electric vehicles, photovoltaics, and sodium-ion batteries. Today, Ms. Laurie will share her insights on the progress of the Tin Valley Initiative and its impact on the industry's future. Please join me in welcoming Ms. Laurie. And Ms. Laurie, the floor is yours.
Thank you very much. I'm just going to share my screen. Hopefully you can see that presentation.
Yes, we can, Miss.
Perfect. So hello, everyone. I'm going to give a brief presentation to introduce two key technology topics. So one is on tin and sodium-ion batteries and on tin recovery from e-waste. So I'll start with the topic of tin in sodium-ion batteries. So sodium-ion batteries, or SIBs, are a promising alternative to lithium-ion batteries. They work in the same way as lithium-ion batteries, just with the replacement of lithium ions with sodium. So there are several advantages to SIBs. One reason being that on a resource level, sodium is more abundant in the Earth's crust, making its supply chain more reliable, which inevitably drives the cost of resources, meaning that sodium is cheap. Additionally, lithium, on the other hand, is a more scarce resource, so their reserves are less than 0.01% of the Earth's crust, with current high demand and supply chain constraints leading to price volatility. Another benefit is that sodium-ion batteries are easier to transport, so they can be transported at 0 volts, whereas lithium-ion batteries cannot, and they face strict regulations due to safety concerns because they have a higher risk of thermal runaway fires compared to sodium, which can be really deadly and difficult to control. Additionally, the use of sodium enables the use of aluminium current collectors at both electrodes, whereas in lithium-ion batteries, they use conventionally copper current collectors. So this is good because aluminium is lighter and cheaper than copper, so we get to have cheaper and lighter batteries. Sodium-ion batteries are also capable of operating across a broader temperature range, making them particularly well suited for regions with extreme climates. And as climate change increasingly impacts global weather patterns, this enhanced temperature tolerance positions sodium-ion batteries as a reliable energy storage solution for diverse environmental conditions. So despite the advantages, the energy density, which is the amount of energy stored per size or weight of the battery of sodium-ion batteries, is still behind that of lithium. So the bottleneck for this is often related to the fact that the research and development is less mature, including research into high energy density anode materials, which is where tin comes into play. So tin plays a crucial role in enhancing anode materials for sodium-ion batteries. Tin has a high theoretical capacity of about 847 milliampere hours per gram, which is significantly higher than that of conventional anode materials. So when tin alloys with sodium, it forms Na15SN4, which offers high volumetric density, which means we can make batteries smaller without compromising on performance, which is great for applications like electric vehicles, where we need smaller batteries. Additionally, not only is tin abundant, but it's also easy to handle with low toxicity and has high recyclability, making it a sustainable choice for energy storage applications. So if we have a look at the graph, it represents some of the current choices for anode materials for sodium-ion batteries in recent literature. So hard carbon is the most common anode material used commercially, but its theoretical capacity is actually less than half that of tins. So we can see the advantages of using tin materials. If we look at phosphorus and sodium as well, they both exhibit high gravimetric capacities, but they suffer from issues including volume expansion, sluggish reaction kinetics, and sometimes complex synthesis processes for phosphorus. And then in sodium anodes, they suffer from dendrite formation. So what I mean by dendrites is they are branches of sodium that are formed inside the battery. And these branches can be sharp and they can pierce parts of the battery, leading to short circuits. So because of these issues, tin appears to be an appropriate choice for a great anode material in sodium-ion batteries, but it doesn't come without its own issues. So one of the biggest issues of using tin is volume expansion. So tin can expand by over 400% during cycling, which can result in mechanical stress and poor conductivity or even cracking of the electrode. So if we look at this anode material here, if this was tin, for example, we could see in the diagram that it would be expanding and expanding and expanding. And eventually it can reach a point where it can crack, which can be detrimental for the battery and therefore can shorten the battery life. Another challenge with using tin is electrolyte compatibility, which you can see in the middle here between the CEI and SEI. This is the electrolyte material where the ions flow through to insert and leave each electrode material. So tin ions, specifically SN2 plus stannous ion, is incredibly reactive and can form thick, non-conductive SEIs when using conventional carbonate-based electrolytes. So these SEIs can therefore reduce the overall performance of the battery and again lead to short cycle life. So what I mean by SEI is the sort of electrolyte interface, which is a layer formed between the electrolyte and the anode material. So you can see it here. So this is actually essential for stopping direct contact between the electrolyte and the anode material, which, if broken, short circuits the battery. So the question is, how can we overcome these challenges? And there have been solutions that have been developed, which is fantastic. So if we look at the issue of volume expansion, some of the methods being used are nanostructuring, for example, which uses very, very tiny nanoparticles of tin, which obviously, because they're so small, have a larger surface area and create a more flexible material. And so because of this, they can better accommodate the volume expansion and avoid cracking. Additionally, we can alloy tin with other metals, or we can form composites with materials like carbon, for example. And these materials can help to buffer the volume expansion by, again, increasing flexibility and also absorbing some of that expansion. So if we look at tin hard carbon, for example, these composites can use porous carbon materials, which essentially has holes in it for tin, which not only makes it more flexible, but also creates a matrix that can hold tin in position. If we look at the issue of reactivity with the electrolyte, there have been some solutions developed, such as the development of glyme-based electrolytes. So these are more compatible electrolytes with tin anodes specifically. So these electrolytes form thinner and more stable SEIs and react less aggressively with tin. So we don't get the same issues that we were seeing with the more conventional electrolyte materials. But it's important to note that tin anode research is less advanced than hard carbon research, for example. But further research and development could boost tin anodes to be even more competitive because of the unique advantages of tin in this scenario. So at ITA, we are actually tracking developments in academia regarding tin anode materials. Some of the most common research materials in the last year include tin selenides, tin sulfides, tin carbon materials, tin oxide, and also elemental tin/tin alloys. So you can see a lot of different examples of tin composites in there. So the graph that you can see on the screen highlights the relationship between specific capacity at varying current densities, and then also an additional layer of information is the size of each bubble. So the size of each bubble represents the number of tested cycles for each material in the literature. But it's important to note actually that some of the materials testing at an academic level could be limited by time and equipment availability. So if we have a look at some of the results on the graph, tin sulfides appear to be a very promising option. So if we look at this specific example of tin sulfide quantum dots on a carbon fiber network, it's been tested at a very high current density of 20 ampere hours per gram. So you can see that it's a lot further on the right-hand side on the graph because it's being tested at such a high current density. It also is a large bubble because it's been tested over a lot of cycles. So it's been tested for 10,000 cycles. And it's able to maintain a specific capacity of over 250 milliampere hours per gram. So what does that mean? So if we look at each different metric individually, performing well at high current density means the material is likely suitable for fast charging and discharging applications, which includes electric vehicles. So the reason for this is because at high current density, sodium ions have less time to diffuse across the electrolyte. But the material that we see here is actually still able to achieve a good specific capacity, meaning that the anode material is suitable for fast ion transport. So this particular example would be great, for example, if we wanted a fast charging EV, which is absolutely in demand at the moment. Additionally, the material was tested for a long number of cycles of 10,000, which is very, very high, meaning that it can withstand many discharge and charge cycles, which means that the material would last for a long time, which would increase the length of time for battery replacements, which is good. So we wouldn't have a vehicle, for example, that needed its battery changing every year or so. It would be a lot longer than that. It's also important to note that in recent academic literature, the most popular choice for tin anode materials has been tin sulfides. The most number of papers on tin anodes the example has been a tin sulfide material. Also on the graph, we can see that on all of the different tin examples, there is actually a form of carbon being used in the anode material as well, which actually does identify that carbon is integral for helping stabilize tin anode materials and buffer volume expansion during cycling. So tin and carbon are really often used in conjunction with each other. On the graph as well, we have a hard carbon example here. You can see this red dot here, which is a lignin-derived hard carbon anode material. So I've just put this on here to compare some of the tin results with a carbon example, which is the most common anode material. So you can see that its position on the graph is a lower current density. It's a lower dot, meaning it's a lower number of cycles, and also it's a lower specific capacity than a lot of the other points. So its position on the graph really highlights the opportunities for high capacity, longer lifetime, and faster charging capabilities when using tin as an anode material. So in terms of development, research into tin-based anodes for sodium-ion batteries has been on the rise, particularly over the past decade, with 995 academic papers between 2015 and April 2025, with that expected to grow in the second part of this year. So of these, 72% originated from research in China, 11% from the US, 9% from South Korea, and 6% from Australia. So again, this highlights China's dominance in the sodium-ion battery field, which is further emphasized by their government backing and resource dominance. And additionally, China are also dominating in the commercial field of sodium-ion batteries with battery giants such as CATL, BYD, and also Heine Battery. We're also seeing additional funding from governments worldwide in the sodium-ion battery market, such as the LENS Consortium in the US, Entice in Germany, and NextGener in the UK, with these projects aiming to advance these technologies in these countries. So this is fantastic for development of sodium-ion batteries worldwide. There are also companies that are implementing tin anodes into their sodium-ion battery technologies commercially. So we have two contacts that we are in touch with. Unigrid in the US and Nanode in Canada are both using tin anodes already in their sodium-ion batteries. We're also aware of existing sodium-ion batteries evaluating tin as a viable option for their technologies. So we hope to see more companies doing this in the near future. So the growing research efforts and increasing commercial adoption of tin and sodium-ion batteries suggests a bright future for this technology, especially in large-scale energy storage and also electric vehicles. Thank you for listening. For a summary, a full summary, a more in-depth summary, you can head to Tin Valley that Jeremy mentioned and go inside of our lounge where we have a Tin AI button here. And if you click on this button, it takes you to some technical summaries on tin and sodium batteries and also tin recovery from e-waste. So please feel free to take a look at that. So I'm now going to move on to a summary on the topic of tin recovery from e-waste. So I think a good place to start on this topic is defining what e-waste actually is. So e-waste or electronic waste is discarded electronics that have reached their end of life. So e-waste encompasses a large range of products from laptops and phones to irons and vapes, or to even EV batteries. So we require electronic products not only for everyday life, but for the transition to cleaner energy. The issue with this, though, is that e-waste is now the fastest growing waste stream globally, with 62 billion kilograms generated in 2022. And of this 62 billion kilograms, only 22% was recycled, with the remainder being dumped or shipped to developing countries without the infrastructure in place to safely and efficiently recycle the e-waste. This is a shame because the metal content in e-waste is actually often higher than that from mining, and therefore efficient e-waste recycling is essential. So where does tin come into play? So tin is actually an essential part of electronics, as I'm sure you're aware, for soldering components and ensuring electrical connections throughout. And in fact, printed circuit boards, PCBs, which are an integral part of electronics, contain an average of 3% tin. So this potential secondary supply of tin from urban mining e-waste is essential now more than ever as the demand for tin rises. Focus, however, in industry is often on the recovery of other metals from e-waste, such as gold, other precious metals, and copper. but people actually are not aware of the quantity of and value of tin in e-waste. So if we look at the global landscape of e-waste generation, it's clear to see that e-waste production is actually highest in Asia. So this can be linked to Asia's large population. But if we look at it from an e-waste generation per capita, so that's per person, Europe is actually the highest, which means that Europe has more electronic devices per person than any other part of the world. In terms of recycling rates of e-waste, Europe has the highest rates. This is due to principles in place such as the extended producer responsibility, otherwise known as the EPR principle, which holds electronics companies accountable for their products once they reach end of life. We can also see from the graph that there are high recycling rates in Oceania, and this is particularly due to recycling giants being positioned within parts of the continent with large populations. So an example is Circle in Australia and also Mint Innovation in New Zealand. But more is needed globally to tackle the rise in e-waste and to ensure valuable metals are being recovered. So if we look at e-waste itself, it comes in many shapes and sizes, and a crucial part of a lot of e-waste products are printed circuit boards. So printed circuit boards are usually concentrated with valuable metals for recovery, and so are targeted by recyclers. So you can find these in phones and laptops, for example. They are made up of roughly 30 to 50% metal and 50 to 70% non-metal, again with an average of about 3% tin. One of the downsides is that they also contain hazardous materials, including lead and flame retardants, that can be problematic for recyclers. So how do we recycle PCBs, and what are the most effective methods? So to start with, e-waste needs to be sorted and dismantled to isolate PCBs for metal recovery. So this can be done manually, but it's time consuming, not cost effective, and also dangerous for workers. So it's highly recommended to be avoided. Robotic and automated machinery is actually the best way forward. And we can also include using spectroscopy methods. So XRF, for example, can be used to identify elemental composition in components to help separate different parts of e-waste based on what they have inside. So once PCBs are isolated and sorted from the bulk of material, there are many, many different processing routes that can be followed to recover tin amongst other metals. So if we look at a direct route for tin specifically, we could use chemical or thermal depopulation, which directly removes the solder material. So thermal depopulation uses heat to melt the soldering material, along with you can use some external force, such as shaking a board, for example, to help remove the PCB components while melting the solder. Chemical depopulation is similar in that it uses chemicals to dissolve solder and recover metals. So actually the International Tin Research Institute, which is now ITA as we know it, collaborated with Ultramex in the past to use ferric chloride and nitric acid to recover tin from PCBs. And in fact, Jeremy was a part of that project. An alternative route to go down is to start by shredding the PCB material. So if recycling companies want to target more metals and go down a different route to bulk recover metals from PCBs, they can start with techniques such as shredding the material. So the perks of shredding the material is reducing the volumes of e-waste, making it much easier to handle as it can be condensed. So if you think about, for example, if we were to place a lot of PCBs into an acid bath or into a furnace, if the material is shredded up and condensed, it's a lot easier to fit more material into the furnace or the acid bath. This is also good because shredded material enables further pre-processing techniques to be employed, such as magnetic, eddy current, and density separation. So what I mean by that is obviously magnetic separation is self-explanatory in that it separates magnetic ferrous metals such as iron and steel from non-magnetic, non-ferrous metals such as tin, copper, aluminium. Eddy current separation actually separates non-ferrous metals from each other based on varying conductivities. So in some cases, we can separate tin from aluminium, for example. And then we also have density separation. So this separates components based on weight, either in an air or water-based environment. So these are really great methods just for initial separations of metals. And the reason this is great is because it makes it a lot easier down the line if we have metals broken up into different groups so that they can avoid interfering with each other as much in later processing. So one of the major metal recovery routes is hydrometallurgy. So this involves using aqueous solutions such as acids or alkalis to recover metals from e-waste. The core steps usually involve leaching tin into solution, separating and purifying the tin-laden solution to recover the tin. So leaching tin from e-waste using acidic solutions requires careful reaction conditions. And actually, simple acids alone can sometimes struggle with leaching tin. And it's found that using an oxidant improves the solubility of tin ions. So, for example, a recent study combined hydrochloric acid with sodium chloride to enrich the chloride content, which resulted in almost 95% tin leaching from the PCB material. But the one challenge really with acid leaching is reprecipitation when tin 2 plus is oxidized to insoluble tin 4 plus. Alkaline leaching, on the other hand, uses strong bases to dissolve tin, forming soluble stannate products. One of the main advantages of this over acidic is it's more selective for tin and lead, for example, and can leave behind less soluble metals in alkaline media, such as gold. Again, in this scenario, oxidants can improve the efficiency of alkaline leaching. And an example in recent research is using peroxides to enhance the oxidation of tin in alkaline media. There are, however, challenges with hydrometallurgical metal recovery routes. For instance, reagents can be costly. Toxic off-gases can also be produced, which means that expensive scrubbing systems are required to meet emission standards. Large volumes of hazardous waste are produced, which can be difficult and expensive to dispose of. And also maintaining precise pH of solutions can be difficult. So another major metal recovery route is pyrometallurgy, which uses high temperatures to liberate and separate metals from e-waste. So pyrometallurgical methods encompass various methods, including incineration, smelting, and also more novel techniques like flash tool heating. So incineration involves burning e-waste in the presence of oxygen, primarily to oxidize and remove organic substances, such as plastics and resins, and then concentrate the metals in the remaining ash. So this is usually a pre-treatment step to reduce e-waste volume and produce metal-rich residue. The residue can be further refined via smelting or leaching. After incineration, tin is often left behind mostly as an oxide or metal particles mixed with other ash constituents. Modern incinerators include off-gas filtration systems, so they can capture any metal-bearing dust or vapor for further refinement. Smelting, on the other hand, is another core method for metal recovery, and obviously is already used at industrial scale. So during smelting, e-waste is obviously melted inside a furnace at high temperatures with the goal of segregating metals into a molten metallic phase and a molten slag phase. So by adding appropriate fluxes and reductants, the smelting process can be tuned so that valuable metals collect in the metal alloy at the bottom of the furnace, while other oxides of less value go into the slag. So industrial smelters can mitigate metal losses by operating under slightly reducing conditions and also capturing those furnace off-gases. Flash tool heating, on the other hand, is emerging as a technique pioneered in recent research by researchers at Rice University in the United States. So in this process, a high voltage electric discharge through shredded e-waste powder raises its temperature by about 3,400 kelvins within milliseconds. So essentially the material is flashed into an extremely hot state momentarily. So this rapid dual heating drives off organic components and vaporizes many metals, and then those metals resolidify as fine particles or condense on the reactor walls. So we get a metal-enriched residue that we can then leach for metal recovery. So this method is actually being trialed commercially by an Australian company, MTM Critical Metals. So importantly, flash dual heating is far less energy intensive than conventional furnace smelting. So while pyrometallurgical methods are effective for processing large volumes of e-waste, they do require high energy input and often result in higher emissions. And additionally, further refining processes are typically needed to extract pure tin. But despite these challenges, pyrometallurgy offers a promising solution for the sustainable recovery of tin, especially as demand grows. So if we look at some next generation innovations that are being explored to recover tin from e-waste, deep eutectic solvents are an example. So they are a mixture of solvents that form a eutectic mixture with a lower melting point than any of the individual solvents. This is great because it tends to use greener solvents and less toxic solvents, but it also means that we can melt that mixture at a lower temperature, and so we don't have to use temperatures as high. And we can tune these mixtures by altering ratios and concentrations to alter its property, depending on our target metal, for example. So this method is being trialed not only in academic literature, but commercially. So in academic literature, for example, academics have used oxalic acid, which is found in spinach, hence the picture of spinach on the presentation, which is able to selectively leach tin from PCBs within a eutectic mixture. So they actually found that they were able to leach 92% of the tin from the PCB in just an hour at 80 degrees Celsius. A commercial example is a UK-based company called DES Cycle. So they are looking to commercialize the process, and they raised over 10 million in Series A funding to do this. Another example is bioleaching, which uses living organisms to extract metals from circuit boards. So we don't need to buy toxic chemicals. We can get living organisms to do it for us. So an example of this in academic literature is that academics use two types of microorganisms to leach tin from powdered PCBs. And in fact, after 28 days, at 31 degrees Celsius, they leached over 96% of tin. But obviously, the challenges that they addressed from this paper were the scalability as a potential drawback and also leaching time. But bioleaching is definitely being trialled commercially. One example is Bioscope in the UK, who are looking to obviously optimize the time and scalability of this process. And finally, one final way to improve the recyclability of e-waste is actually adapting the design of PCBs themselves. So this is being explored by several companies globally. One example is Jiva Materials in the UK. So they specialize in their solo board design, which is a PCB made of materials that can dissolve in hot water. So this is fantastic for the recyclability of the metals. So their solar board has a 67% lower carbon footprint compared to traditional technologies. But one drawback is obviously the cost to manufacture more sustainable PCBs, which does make them less competitive. And also they need to be designed to endure heat and moisture effectively. So further optimization is likely needed. So if we just quickly look at the research and commercial activity in this area, academic papers have been on the rise in the last 2 decades. The 3 countries with the largest number of tin recovery papers are China with 25%, India with 13%, and South Korea with 8%. So actually this highlights that there is a high concentration of research in Asia, which funnily enough is the region with the highest e-waste output. There are also e-waste recycling facilities populated all over the world, with this industry growing year by year. So some examples include Arubis in Belgium, who are known mostly for copper recycling, but they are also a tin and partially an e-waste recycler. Circle in Australia, they're actually Australia's biggest e-waste recycler, and also Ataro in India, they're India's biggest e-waste recycler. So not only are companies doing this, but there are also collaborations between institutions and organizations working on this topic. For example, there's a collaboration between the French Alternative Energies and Atomic Energy Commission, or CEA. They're collaborating with Nanyang Technological University in Singapore on the topic of smart sorting of e-waste. So actually, someone from the Scarce Alliance presented at one of our conferences last year. So if you're interested in watching that, it's available inside Tin Valley. So there are also regulations in place in regards to e-waste. So in the EU, a regulation related to the destruction of persistent organic pollutants, otherwise known as POPs, has been adopted. So POPs are chemical substances that do not break down easily and can therefore accumulate and risk being harmful to both human health and also the environment. And there are POPs inside e-waste, inside printed circuit boards. So the EU regulation states that these POPs need to be destroyed thermally during the e-waste recycling process, so to minimize their risk. But this obviously can be a challenge for e-waste recyclers that are not using thermal treatment. So regulations like these add another level of difficulty to e-waste recycling. So again, if you want to read a more in-depth summary of this topic, you can head to the Tin AI section in our Tin Valley Lounge, which is free for academics, and take a look. But thank you very much for listening.
Thank you so much, Miss Laurie, for another insightful presentation. We will now open the floor for questions and answers. If you have any question, please type them in the chat box or use the raise hand feature on Zoom. But before that, please fill the Google Form survey on the chat box before asking a question. Another thing is, since most of the audience is Indonesians, you can post your questions in the chat in Indonesian, and I will help translate it and communicate it with the speakers. Jadi apabila ada audiens yang ingin bertanya dalam bahasa Indonesia, bisa diketikkan di dalam kolom chat, lalu akan saya bantu terjemahkan dan komunikasikan ke pemateri hari ini. Okay, while the audience fill the survey, I would like to start with my own question first. As previously mentioned, that Indonesia is a major player in the tin world, but from what I've gathered in my study, Indonesia still primarily export tin in its ingots form, while the final products such as solder are still small when compared to ingots production. So my question is to the speakers, what steps Indonesia needs to take to unlock the full potential of tin industries? Thank you.
Well, that's a very good question. I'll answer that if I can. So you're absolutely right, which is the need for increased downstream industry building in Indonesia for tin. That is, government has made that very clear. You're right that solder is the most obvious way to do that. Chemicals is another way to do that. PDT have a chemicals plant making firstly stannate chloride, but then PVC stabilizer. But that's a very difficult area to go into quite easily. So I think that the solder area is the most obvious. And for me, the most obvious application is in solar. So I showed you, for example, that tin is used in solar panels. I showed a picture of that, which is a copper ribbon coated with a tin lead solder. That's a high volume, very relatively low technology route. So that would be my suggestion, for example, is to look for those kind of large scale applications that require a low level of technology like solar ribbon.
Thank you so much for your clear answer. And I would like to move to another audience that would like to ask a question. Mr. Dede Firmansyah, Please, if you will have the floor.
Hello.
Hey,
Hello.
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 Good
Yeah,
to see you.
Okay,
Hi.
good to see you. Hi. Hello, I'm Daddy. I'm a master student now, and then my research is focused also in energy storage. And I'm really interested about the high energy capacity that you can produce from your sodium ion battery. It's around like 847 milliamp per hour per gram, right? And then you have like longer cycle life up to 400%. And I see that this is in the future battery, and that can we as a tin production country can see it as a potential in for the future. What I want to ask is, from your presentation, you say that we can use tin use as electrolyte for the sodium ion battery, right? And I see that tin can use in various form. Even you can use a nanostructure on your battery. So I just want to curious about if possible if we can use the tin not from the metallic tin, or we can use from the tin oxide also. Because if we compare with the lead acid battery, right? Lead acid battery has really much cheaper cost production than tin production metal. So that is my question. Can we use another form of the tin for to produce tin as electrolyte in the sodium ion battery? Thank you.
Georgia, I'll take that first, and then I'll pass to you, Georgia. So yes, I think that your question is a very good question. And you're right that there's a large variety of different kinds of tin materials that can be used here. And you're also correct that tin is a relatively low technology compared to, for example, silicon or some of the other more difficult materials to work with. I would say that, and this is partly an answer to the previous question, is that you can use tin metal. You can use, that's mainly a lot of work was done in India using this tin particles or tin foils. But then as you increase the technology, and you're quite right, some have used tin oxide, but mainly tin sulfide is more, as Georgia has shown, better. Then you get more sophisticated. But when you see some of the materials like Georgia showed there, which are nano particulate, where you're impregnating the carbon with chemicals, then your chemistry gets very complex. So it's quite complicated chemistry at that level. So there is a whole range, and you can use different kinds, including tin metal, but it depends really on the level of technology you have and what you're prepared to the amount of science that you can put into it. George, you want to answer this a bit?
Yeah, just to add on to that a little bit more, if we look at some of the recent academic papers, a lot of academics are using different tin chemicals to synthesize these tin anode materials. So tin chlorides, tin hydroxides and things. So it's varied paper by paper, but a lot of the tin raw materials are tin chemicals.
Yeah. Yes, that's right.
So I'm sorry. My next question is about if you can use the tin from the tin oxide, right? Because we have like different type of ore in the like in the green, in the blue, and then in the red tin belt, right? It's like a different specification of tin, or we can see if, for example, in the Indonesian tin, we have like ilmenite, we have a zirconic, and then we have another compound of the ore. So, I mean, if it's possible, if we use the tin oxide from Indonesia.
I think if you're maybe asking, can you use the cassiterite ore directly from the mining? I think the answer is an interesting one. I think that would be quite unconventional idea, because you'd have to separate the tin oxide from the rock. But I also do know that in Indonesia, especially in the primary formation, that the tin is very fine. The tin oxide is very fine. So I'm kind of interested in that idea, but I don't think we've ever seen anybody do that without processing. Normally, most people who use tin oxide will make it from the tin ingot by chemistry to dissolve the tin and then precipitate in chemical rate, rather than directly from the ore in the way that I think you may be suggesting. I'm interested in exploring all of the ideas, but I think that would be an unusual one. can I just mention something? Is that okay? Somebody mentioned tin batteries, so I'm just going to put into the chat a link there. If you look on our website, you can see lots of different technology stories actually, and this also is one we just published about tin batteries. So this is using tin metal and just water. So if you, in answer to your first question, maybe you should look at this one as well, because this is a very low technology way, and some very interesting work here on tin batteries, just using tin metal and aqueous solutions. So that's answering a number of questions at the same time.
Okay, thank you so much for another answer. There's another question from Danang Wiprasetyo earlier that he is wondering about the potential of tin/nanocarbon composite materials in the world.
Yeah, tin nanocarbon, did you say?
Yeah, tin nanocarbon.
Yeah. Yes. Well, tin nanocarbon, many of the products that Georgia showed were tin carbon products, where you're impregnating tin chemicals into various different carbon products. And for sure, the nanocarbon products would be even higher surface area. But I think that here you have to bear in mind that nanocarbon is quite more difficult to handle. So the more nanoscale you go, the better technology, but it's harder to handle. And you also have to think about scale up and commercialization. So when you're scaling up nanocarbons, they are more expensive to make in volume, and they're harder to handle. They have health and safety issues and so on. So there are definitely, you're likely to get better performance perhaps, but the chemistry and the physical chemistry gets more complicated. The scale up is more complex, I would say. So yes and no.
Yeah, I think it's also important to note that there are examples of tin anode materials that aren't using nanoparticles of tin that are successful. So it's not essential for you to use nanoparticles of tin. It's just one way that some academics are mitigating some of the volume expansion issues. But there are also successful stories commercially and academically where they're sort of using micron-sized tin, for example.
Okay, thank you so much for another answer. If there's any more questions from the audience, please feel free to raise your hand or use the chat box. Oh, there's one actually from Mr. Hiskia Dewanto. Thank you for the comprehensive explanations. How about the tailings or waste from tin extraction process? Is there any new innovation or development for tin waste recovery?
Yes, I mean, this is very important commercially. There are many tailings projects. There's one in Peru. I think there's a new tailings projects going into China just now. Yes, using leaching or hydrometallurgy methods here. Yes, there are other like tantalum or other high value products inside the tailings as well as the tin. Personally, I would be thinking about using maybe carbochlorination. So instead of I mentioned this technology briefly previously, where you combine the materials with carbon, and then you add chlorine gas. And when you do that, you get stannous chloride. The chemical is directly from the ore. So that's one technology that I would recommend here to look at. But so yes, I think there are many possibilities of looking at tailings and waste, and I'd like to talk to any of you who want to look at that.
Okay, Mr. Dewanto, are you satisfied with the answers? Okay. Another question for Mr. Hassani. Sir, what if a tin producing country like Indonesia decides to hold back exports to push price up, but then developed countries speed up research on tin alternatives and actually succeed? Wouldn't that strategy backfire on us when we end up regretting it? Thanks in advance.
Well, I know this is more of a market question for sure. You talk about tin alternatives, but actually, I would say that it's not very easy to substitute tin. So I don't think that for the major uses, there will be any tin alternatives very easily. The major use we mentioned was in solder, for example. There is no other way really to make electronics or replace solder to already expensive already. So people only already use tin because they have to. They don't want to. It's too expensive already. So the reason they use it is because tin is the only one technically that can do all of the different things that it does. And so that has always been true. And I think it will still be true if the price goes up in the way that you say. So no, I don't think it will have a seriously big effect. If that happens, the tin is very robust to substitution.
Okay, Mr. Hassani, is the answer satisfied? If there's any more questions, you can post it on the chat box or raise your hand and ask directly.
We're very happy to be in touch with you, and anybody who wants to be in touch with us can either go to Tin Valley or be in touch with us individually later. We'd be very welcome to talk to you.
So,
Especially, sorry, I was going to say, especially we'd like to help you support some collaborative projects in Indonesia. It's very much a part of our wish that we can start to do some collaborative projects in Indonesia on some of these topics together. So we're very keen to talk to you about that if anybody wants to work with us on that idea.
okay. So, Jeremy, I have a question for you and for Gregoria. For you, can you explain the difference between strategic and critical minerals? And what about the tin position in these matters? And for the Gregoria, maybe I want to know about the interface between the electrolyte and the electrode. So what is the direction of the research on this subject? Thank you.
Okay. Okay, on the question of critical minerals, it's obviously a very growing question. People are more and more focused on it. As I mentioned in my presentation today, it's not only important how much tin we have, but where it is produced. And I'm sure you are very aware of that. What we are seeing is that people don't yet understand how important tin is. That's a very big point. People don't realize tin is used in electronics, for example. So there's a big work we need to do together to make people understand how important tin is to everyday life now and to the future. So that's the first point, is we need to tell people that. The second point is I think that we are seeing that now the supply chains are shortening. What that means is that we are seeing people putting new capacity for smelting into Africa, for example. And also here in Europe, there's a discussion of putting tin smelter here in Europe. And I think in the US, it's more urgent. They want to put more smelter capacity into the US. So I think that we will see the shifting of the production locations in the future. We're already seeing that happen as a response to the critical minerals question. But it's a very important one.
In terms of a response to your question regarding the SEI layer, I think you're asking about. So this is the solid electrolyte interface layer. So it's formed during early cycles within the battery, so charge and discharge cycles. So it's formed by sort of decomposition of the electrolyte, which forms this layer between the anode and the electrolyte. And it's essential for essentially protecting direct contact between the electrolyte and the anode material, which obviously if they're able to come into direct contact, the battery can short circuit. And there's also a layer formed between the cathode and the electrolyte that's called the CEI as well, which you could see on that diagram.
Yes. Could I just mention that if you go into Tin Valley and go into the on-demand presentations, you'll see I gave a presentation in there on tin chemistry. So I bring that to your attention because in answer to the question that Georgia gave and your question about the SEI, the role of the tin 2 plus ion, the stannous ion, is very important in that reaction with the electrolyte. So to get this chemistry right, you need to understand tin chemistry. Especially the role of the tin 2, the stannous ion, is very important. So I recommend, if you want to know more about that, look in the Tin Valley in the on-demand.
Thank you for the answer.
Happy to answer any other questions if anyone has any.
Pak Balga,
Yes.
so maybe it's time to close
Okay.
the webinar.
Since the time is up for us, thank you so much for attending our webinar. And again, I would like to express our sincere gratitude to all our speakers for their valuable contribution and to all participation for their active engagements. We hope today's sessions has provided you with meaningful insights into teen industry and its product development. Once again, we extend our heartfelt thanks to our supporting organizations, and your support has been instrumental in making this event as a success. Please stay tuned for our upcoming webinars and feel free to reach out with any further question or feedback. Thank you once again and have a great day. Thank you.
Thank you. Our pleasure.
Thank you very much.
Thank you, Jeremy and Georgia.
Okay, thank you to our moderator. And all of our speakers for the valuable insight and through provoking discussion. We hope this session has grown your perspective on the importance of teen industry and the innovation shaping their future. Until next time, thank you for all our participants for your time, attention, and enthusiasm. And until next time, take care, stay safe, and have a wonderful day ahead. Thank you.